A vertical container with a base area 14 by 17 centimeters is being filled with identical pieces of candy, each with a volume of 80 millimeters cubed and a mass of 0.04 grams each. We want to assume that the volume of the empty space between these candies is negligible, and if the height of them is increasing at a rate of 0.5 centimeters per second, at what rate does the mass of the candies in the container increase? You want to start by expressing the thing that you're being asked for in perhaps different units to start, but then we can convert the units into what we need. So I just always look for, what are they asking me for, They want a rate of mass of candies increasing in kilograms per minute. All right, so you could start with just that the rate that we're looking for would be a mass divided by a time. We see that we're given the height of the candies is increasing at a certain rate of 0.5 centimeters per second. So this is what we want. And then what we have, though, is a speed, basically. And what is a speed in physics? Distance divided by time. So we know the area of the base, which would be just a length times width. So that's going to be 14 centimeters by 17 centimeters. But I don't like to work with centimeters. You could just do this. 14 times 17. But this is going to give us centimeters squared. So we just want to automatically convert that into meters with this conversion. There's 100 centimeters in a meter. But not only that, but you have to square the factor that you introduced because of the 2 centimeters there. Alright, so let's see what that area is. Looks like the area is 0.0238 meters squared. Alright, so let's draw it. That's what I like to do. Let's see if we can draw what's happening. Alright, so you have this base of area 0.0238 meters squared. And there's a height of candy that's steadily rising. I'm just going to draw it halfway up the column, That thing would have a height, h. But not only that, but its height would be changing with time. And so a lot of times we like to draw just a little piece of the change, And we could say, while the height of the candy has height h, the height of that little piece would be, in calculus, it would be dh. Not only that, but that piece would have a volume as well, dv. And then the overall candy depth would have a volume too, but that would be called big V because it's not infinitesimally small. It has some substantial volume, right? Let's see. So how is the speed related to dh? Well, you'd say that the speed could be written as dh over dt. The change in the height of the column with time. And so it's going to be 0.5 centimeters per second, but I don't want it in centimeters, right? I'm going to change it to meters. So that's going to be 0.005 meters per second. All right, now they want to know the relationship between this and this. So we have a formula for the volume of candy in that thing, length times width times height. All right, so in calc what you would do is you would differentiate both sides. But the thing is that the length is going to be constant and the width is going to be constant, right? They're not changing, but the height is, and the volume is too. So there's many ways to write that, but one way you could write it is you could write dV over dH equals L times W, and then you remove the h, right? Because you take the derivative of it. But you could also do that implicitly, and you could basically multiply the dH to the other side and write that dV equals L times W times dH. But anyway, what I want to do is I now want to come in and divide both sides by anything of my choice, but I pick dt. Because it makes it into a relationship between the rates. Alright, so I know what the length is, I know what the width is, and I know what the speed of the rise of the candies is. So I can plug in. It was 14 centimeters, which is 0.14 meters, 17 centimeters, and then times 0.005 meters per second. So let's see how the volume is changing with time then. Okay, so that's going to be meters cubed per second. Units work out nicely. But it isn't exactly what they're looking for just yet. Because they did say that they were looking for mass per time, not volume per time, right? So we want to use a physics concept called density. And density could have the letter D or rho, which would be sort of like a cursive P. And that would be the mass divided by the volume. So if we rearrange the formula, the mass is the density times the volume. Alright, then we could do that differential idea one more time. Do it on both sides. So dm equals rho times dV. The density is just like a property of the candies. That's not going to change. It's going to be constant for this problem. But now let's divide both sides by dt to get the relationship between these two rates. So on the one hand you have how the mass is changing with time, and on the other hand you have how the volume is changing with time. But I already found how the volume is changing with time though. So now I could plug in if I know the density though. And then I could find what they're finally looking for, which is dm over dt. So what is the density? I have to go back to the problem. Well, they tell you the volume of a particular candy, and they tell you a mass of that particular candy. So using those things, we can find the density of the candy. Alright, so on the side here, let's find the density of the candies. It would be found by dividing the mass of one candy divided by the volume of that candy. So 0.04 grams divided by 80 millimeters cubed. I don't love those units though. I'd rather have them in the standard units that we always work with, which would be meters, and actually kilograms, believe it or not. You'd think grams would be just like the base unit, and that's what we would use, but we actually use kilograms more than grams. So I'm just going to, out of habit, I'm going to switch it to kilograms. So put grams on bottom, kilograms on top. The prefix kilo stands for 1,000, so we can put 1,000 down here and a 1 up there. That'll take care of the mass units. In fact, they even said they wanted it in kilograms, you know. But let's change the millimeters as well. We don't like those units at all. Put millimeters on top, meters on bottom. The prefix milli stands for 1,000th, which is of course 0.001. But what you would do is you'd put the 0.01 down here, because that is the definition of what a millimeter is, 1,000th of a meter. But of course, we see that we've got millimeters cubed, so we can't stop there. We actually have to cube our conversion factor here. So the density ends up being, looks like 500 kilograms per meter cubed. Alright, now that we have that, we can plug it in. And let's plug in our rate that we found above. Alright, so this is going to give us kilograms per second. Which actually is a unit that we like in most circumstances. However, they do ask it in kilograms per minute for whatever reason. So we'll just do one more conversion. Get the units that they ask for. I'm going to want minutes on bottom. So throw that in. And then put seconds on top. That way my denominator units will cancel this time. It'll produce the denominator units I want, which are minutes. But I just got to know that there are 60 seconds in a minute, of course. 3.57 kilograms per minute.